Okay, so we are being recorded right now. So I think we can start. So, okay, let's start. Okay, so hello everybody. This is Luboš Pirkl and Radek Máca from CFD Support. Hello Radek.
Hello Luboš, hi.
Yeah, so welcome everybody to the webinar on Turbo Machinery CFD, which is Turbo Machinery CFD is a smart, easy and affordable CFD software for rotating machinery. Yeah, and yeah, I'm a little bit ahead. Okay, so I hope everything works well. Anyway, in case of any technical problems, feel free to contact us in the future, and we will gladly answer all your questions and comments. The webinar is being recorded, and its recording will be made available on our YouTube channel later or afterwards. Yeah, and the topic of today's webinar is the Francis turbine, and I think it's time to get to the action. So let me start with who we are. So please let me introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support and also a managing director. Today I'm here with my colleague Radek Máca. So hello, Radek.
Hello again. Hi.
Yeah, hello again. Hi. So how do you feel today?
Yeah, I have great times because tomorrow we have a bank holiday, right? And the day after tomorrow. So this is we can say goodbye party with the work
Okay.
this week. So I'm very fine and looking forward for this webinar.
Okay, so we all are fine, so that's great. So I will only say that Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of our today's webinar. So this is two of us. I think we can switch the camera off right now, and let's go ahead. So about the webinar program, the webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be 3 parts in this webinar. In the first part, I will give the general introduction to Turbo Machinery CFD. I'm going to point out the main Turbo Machinery CFD features and also benefits. In the second part, there will be a live example where Radek is going to show you how to simulate the Francis turbine in Turbo Machinery CFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window, or you can even send your questions to an email to info@cfdsupport.com, and we will answer all your questions later in this webinar. Especially in the beginning of the webinar, I'm going to be quite general, or we're going to be quite general, but feel free to put your questions and we will gladly answer all your questions in detail. Okay, so I will start with CFD Support. I will go just quickly. So the CFD Support is a private engineering company dealing mainly with computational fluid dynamics. We are located in Prague, Czech Republic, and we are used to deliver complete engineering, CFD engineering projects. We do projects on demand all across the CFD field. We also do quite lots of outsourcing work. We deliver extensive open form training and consultancy, as well as open form custom development and open form support. And of course, our flagship product is Turbo Machinery CFD. And yeah, that's what's today's webinar about. Which brings me to Turbo Machinery CFD. Let me give a brief description. What is Turbo Machinery CFD? So Turbo Machinery CFD is a unique software based on OpenFOAM, and it was designed for CFD simulations of all rotating machinery, such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, and many more. It was designed both for radial and axial machines and also for incompressible and compressible fluid flows. Turbomachinery CFD is complete CFD workflow, a CFD package that covers all the engineering steps from the pre-processing over the simulation to the very detailed post-processing of the results. Turbomachinery CFD is independent on any other software, and on the other hand, it's fully compatible with standard OpenFOAM. Please let me put just a quick review of its unique value proposal. So we believe Turbomachinery CFD is unique at least for 4 reasons. Number 1 would be Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. This gives the investment into Turbomachinery CFD a permanent value, of course, and this also means our clients can scale their CFD simulations in a really big way. Number 2 would be Turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results, it can be run by a single click or a single command, and all the process is being done automatically. So for this reason, Turbomachinery CFD is extremely effective because it's automated, and you can generate the results very fast and in a very smooth way. And number 3 would be we believe we deliver extraordinary technical support. We are proud of it. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in it. And also we support our clients even in matters out of the turbomachinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. And the last one would be the real tutorials are included in Turbomachinery CFD, so the Turbomachinery CFD user has no doubts about the best practice settings. There are included the real machines that are already preset, so basically the user can take the tutorial and just replace the geometry and the settings and run the simulation. So it's ready to use, and the best practice is included. There are many other benefits of using Turbomachinery CFD. I'm not going to go for all of them. Yeah, I'll just join a little bit of or a few technical details. So Turbomachinery CFD is available both for Linux and Windows. The workflow is exactly the same in Windows and in Linux. So this is what is of course missing for example for standard OpenFOAM. Nowadays, 100% of workflow of Turbomachinery CFD is in graphical interface. So no need of running anything in command line. 100% of workflow is covered by the graphical interface. The graphical interface is ParaView. Of course, the command line is possible, and many people still use it, but most of the users nowadays use the graphical interface because it's very intuitive and very usable and efficient. And Turbomachinery CFD is very transparent. The trial version is available for free for 1 month period, so anybody can try Turbomachinery CFD, and afterwards he or she can decide to go for it or not. So the demo version is available, full version. The real tutorials are available for all the important machines. There is one tutorial to try to test the workflow, how it works. Yeah, every single simulation has its HTML report. So the report with the results is created out in an automated way, and anytime during the simulation, anybody can watch the results in a web responsive HTML report. So it's very effective this way. And Turbomachinery CFD also includes TurboBlade Post, which is a special set of libraries for ParaView for post-processing of turbomachinery, like blade-to-blade view, material averages, and few more. Workflow is fully automated, and it can be scripted further in Python. So if someone wants any feature which is present in OpenFOAM. It can be edited by a single Python script. So it's very flexible, very usable in this sense. And perhaps the most important information from today's webinar is all the information on all the resources are available online on our website. So you can take a look on our website and you can learn a lot. And of course, you can send us an email. We will answer everything with a pleasure. It's our job and a pleasure. Okay, I think this is time. This is time for the live example. Basically, that's the reason why we are here today. So, Radek, may I ask you if you're ready with your live example of Francis Turbine?
Yes, I absolutely am. So
okay,
you can.
Okay, that's great.
You can hand me presentation.
Okay, I will. So I'm making you organizer right now.
Okay. So now. Yeah,
yes.
You should see my screen.
Yes. Yeah, we see your desktop. Yeah.
Great. So,
yes.
Hello again, this is Radek speaking, and I will directly start with the practical part because Luboš has already said a lot of useful information and technical details about, or general details about the TCFD, so I will directly start working with the TCFD. Well, so today's case will be, or is the Francis Turbine. So I will directly run the graphical user interface using this icon. So I am using TCFD, the brand new version of TCFD, which is 17.06. So I will just click on the icon to start working with TCFD. So as you can see, the para view appears directly. And now here, who knows ParaView in the default. So now there is automatically loaded this TCFD source using which we can set up whole computational process. So using this TCFD source, which includes a lot of menus directly here, we can set up the CFD computation using our software TCFD. So what do you need to start to working or to set up in your case is to have the geometry. So I will start here in the components part in which we define the geometry, and today I will really start from the scratch. So at the beginning, I will have only, where is it? Francis geometry only. So I will have only the geometry files in the STL format. And now I just I will mention how it should look like. So basically, the methodology of creating the mesh for rotating machines is that the main part lies in decomposition or creating your machine into several main parts, which we call the components. So this is the input geometry. Yeah, each color defines a separate STL file, which clearly defines each part of the geometry of the Francis turbine. And this part must be split into several components. So in our case, we have split the overall geometry into 3 parts. So first part, this spiral part with the guides blade. So is the component 1, let's say. Then we have the rotating part with the rotor. It would be the component 2 rotor part, and the draft tube or the outlet part from the domain or of the domain is the third part. So as you can see, these components are defined separately using these STL files, and as you can see, there are the interfaces between each component. So each component has to have each interface. So basically, each component has to be watertight. Yeah, so it's to be closed surface, and this is how the input geometry should look like. And this holds for every type of machine, for compressors, turbines, fans, and so on. So this is the original setup, and here I just would like to visualize how the components are created or should be designed and created. and export it from any CAD program and so on. So back to the ParaView. So now I will start to setting the computational mesh. So as you can see, or as you saw, that we have 3 components. Here in the components part, there is a nice graph or the topology of our current machine, our current setup. So how we can start? So geometry source for us is a directory with the STL files. We have 2 more options. That is, we can have one multi-solid STLs, which is quite similar to the directory with separate STL files. And also, our software provides external OpenFlow mesh. So it means you can use almost any external meshing tools, meshing program. Then the mesh is converted to the OpenFlow, because OpenFlow implicitly provides a lot of utilities, or how to say, converting tools for a lot of mesh formats. So we can also use some external OpenFlow mesh, and the definition will be similar. Okay, so we have the directory with the STL files. Now I should found this directory, so I have placed it into the OpenFlow directory. Because I'm using 17.06 version. This is my user directory. Here I have Francis Turbine, Francis Geometry only, and this STL directory. Now, as you can see, all the geometry which is in this directory is loaded in this list. And now I should aligned, or I should set each, or to each STL, I should set the type of the boundary for the CFD simulation. So what I didn't mention here is the component name. So I can define it as, for example, as a spiral, to be more clear which part I am using. So now you can see here that really the spiral appears here. Number of periodic segments is 1. So the software also provides to simulate, for example, on the turbine, axial turbines, you can simulate just 1 blade segment, and afterwards you have to set here the overall number of blades, which defines your wheel. Yeah, so if the geometry will have 50 blades, so you can define, and your input geometry has only 1 segment, so then you should define here the number of blades. But this is not the case, and now we will go to assign correct type of the boundary to each component. So we are starting with the spiral, so which is this upper part. So I will start. So I need to find the proper STLs. So for example, the inflow is really the inlet to the domain, and it should be defined as the inlet. So real physical inlet and outlet to the domain should be set as an inlet or an outlet. So in this case, this is the inlet. Perfect. So inflow with the inlet, and if you click on apply, and then you click on this eye, which is now invisible, but if you click on it, it makes it visible, and you can see the first defined part of the geometry, which is the inlet. So now I should go on. For example, here is the spiral. So spiral I can define as a wall because it is the rigid wall. Again, I can click on apply to really see what I have added, what I have just added. Right? This is this. The next part I know is the spiral dip, which is I can define it as the wall or as a blade, because as you will see, it is a blade which is splitting this spiral or this inlet volute. So as you can see, yeah, this is this part, and I can go on. So there is yeah, guide. The guide is also belonging to this part. So the guide blade, I can define as a blade. Guide hub I can define as a hub, which is here. The same holds for the shroud. I can define as a shroud. So now I can check if I edit proper STL. So I just click on the apply button, and now I can see that almost all there is. So now I have to define this outlet interface, and it is named as interface. So this is the interface from the spiral to the rotor, and here is the name as a draft. So this draft to rotor interface I have to define as an outlet interface. So any interface, any part which is connected to the next component should be defined as the outlet interface or inlet interface with respect to the direction of the flow. So this is the outlet interface, and this outlet interface must be connected to some other part, some other component. So by right click, you can the new box appears, and you should assign to which component it should be connected. So this is the first component, and it should be, or it must be connected to the second component. If I click on it, then you will see in this topology graph that really my outlet interface is pointing to the second component. So I click on apply to see if my first component is well defined. Oh, and you can see that it is not correctly. So this is interface from draft to rotor, so it is not correctly defined. So I should not use this one, but this is the guide. So from the guide to rotor part. So again, this is the outlet interface. I should connect it to the second component, and again I will click on apply to see if now it is correctly defined. Yes, and it is, so perfect. Okay, and now I can go to the component number 2. So component number 2, again I will find the directory. Yeah, it is still in memory, so just I will click on the OK button. Component name will be, for example, rotor. And yeah, now you can see here perfectly, and now I should assign the rotor parts of the geometry. So for example, here I have rotor blades, so I should define it as a blade. So I will just click to see if this part is really defining the blades. Okay, so I didn't click. Okay, now I clicked. Yeah, perfectly. And what is nice to use here in the visualization tools, use this VTK block colors, because then afterwards it will be colored with the same colors as this graph, topology graph shows. So now we can see that really rotor is the red one, and we can see this red one parts. So in the same way, I can continue. So here is the rotor parts of hub and other parts. So hub rotor tip, so it's part of the hub, so I can define as a hub. Again, hub rotor wall, so it is part of the hub, and hub rotor wheel, again, as a part of the hub. All right, then there must be some shroud, which is here. Perfect. And the outlet, which is our outlet and inlet interfaces from the rotor. So this is interface from rotor to the draft, which is the outlet from the rotor. So it must be defined as an outlet interface, and the same holds for the guide. But in this case, it will be the inlet interface. Perfect. So I will click on apply to see if I defined these rotor parts correctly. Great, and as I can see, this topology graph, I forgot to connect these interfaces. So the inlet interface must be connected to the first component. Now I see the solid line, also solid arrow, which shows me that the connection is properly defined. And the same I have to do for the outlet interface, so it will be connected to the component 3. Great. And the similar I will do for the component 3, which is the draft part of my geometry. So I will go for the last component. So again, I should load the directory, and now quickly I will define this draft tube. It is composed only from 3 parts, I believe. So the first part, the inlet, is the inlet interface. So from the rotor to the draft interface. So it is the inlet interface. So again, I will just click on it and see if this is really the inlet to the last component. So now it checks these STL files. Yeah, and we can see here that really this is this interface. Perfect. Then we have this draft tube. So we can define as a wall because it is really wall, and the outflow from the geometry here, the outflow. So this have to be the outlet type. So now I hope I defined it correctly. So we can see it in a few moments right here in this render view. Perfect. This is what I need. And as I see in this topology graph, something is still missing. So to connect the component 3 or the inlet to component 3 to component 2. Well, perfect, solid line. And okay, I can define the name to the draft tube, for example. Great. So this was the assignment. This was an assignment process. So to assign the real physical type of boundaries for CFD simulation for every STL. Perfect. So now I am satisfied. So I can close it, this topology graph, and go on. So what are the other parameters to set for the geometry? Here, as you can see, you have to check which component is rotating. So the second component is rotor, so the second component should be rotating. So I have to click this rotating component. And of course, you should check here in this column which part of the geometry is physically rotating. So of course the blades, because the hub is connected directly to the blade, so the hub must also be rotating. And in this case, because this is not unshrouded case, there is no clearance between rotor and shroud, so shroud in this case is also rotating. Perfect. So this was about the rotation, how to define the rotation. And now there are important parameters to set. So it is so-called background mesh size. So it is a size of the largest cells in your computational mesh, which will be created afterwards. So usually you have to know what is your dimension of your geometry, which you can see, for example, here by visualizing the access grid. But the engineer knows the sizes of their geometries. And for example, here, I don't know, we have component 1, yeah, component 1. So some reasonable size could be, for example, in this case, for this tutorial purposes, for example, 0.12 meters. So it means 12 centimeters will have the largest cell in the domain for component 1. Well, then what is the really important parameter is internal point, using which you really tell which part of the geometry will be meshed. So basically inside of your component or outside. So clearly we need the inside of the component. So again, you should know the point inside. You can clearly found it here using, for example, the sources and point source. then you can move this point really inside your spiral part. So now I have clearly, now it's hidden, so it's clearly inside. And if you check this point source, you can read these coordinates directly here. And to set it, to copy it and set to the setting parts, to the setting part of this internal point. So simply in this way, and the last one is that coordinates here. Okay, so I will click on apply just to check if everything is okay and no error will be thrown. Okay, and this is done basically for all parts, for all components, so also for component 2 and component 3. So I will don't do it right now, and then afterwards I will use some template. But basically, this is the main step you should do during the definition of the geometry and of computational mesh. What I didn't say, so background mesh is the largest cells, and then for every patch, for every boundary, you can define the levels of refinement. So automatically it is preset. So for example, for inlet, there is no need to refine the mesh, and for the walls, type of walls, there are preset values 1 and 2. But for some computational similar, or for some, let's say, mesh convergence studies, you can play around and look what is happening with your results. Okay, so this was about the mesh, and now the other menus, using the other menus define the parameters of the computation. So basically, here in the general part, you can save this current setup. So I can save it as, for example, my setup, and anytime it can be loaded again or used for another similar geometry and so on. So what is important here, we have to set the machine type, right? So we provide several machine type: compressors, fan, pumps, turbine, and water turbine. So this is water turbine. We have to set the proper coordinate system of the rotation. You can see that the Z geometry is pointed, or the axis is really in the Z direction, which is properly defined. And I know that the origin really lies in 0.000, which is standard approach when you are creating the mesh with the rotation or the geometry where something is rotating. Well, in the geometry scale factor, it means if your input geometry is in millimeters, you should define the scale factor in as a 0.001 to scale your geometry, your input geometry, to the meters. Some other parameter: every time you point any box, you can see a hint, which is really useful, and you can clearly read what can be changed by this variable. In the physics, fluid name is water, which is automatically set for water turbines. You can use fluid defaults, or you can change it. So fluid defaults are dynamic viscosity of this value and reference density of this value. We provide cavitation risk, so you can enable the cavitation risk, which computes some additional post-processing tools, which tells you, for example, how many cells inside your geometry or how big volume can cavitate, and so on. Of course, you can define the turbulence model k omega SST. If you prefer to set or modify the parameters of k omega SST, you can apply this advanced button, but this is really advanced parameters, so I will hide it again. Inside the speed lines, you really define the operational points which you would like to simulate. So basically, speed lines define different speed of rotation, so it doesn't make a sense for water turbines usually. And my speed of rotation for this geometry is, I believe, is 600 revolution per minute. You must be careful on which side your rotor is rotating. So basically, it follows the right hand rule, where your thumb is pointing the axis, and your fingers shows the direction. So I believe in this case, this is rotating well in this manner. So I have to set minus 600 to set the proper direction of the rotation. Okay, then you can define several points with different condition, with different operational points. Each point should have maximum number of iterations. So usually, for example, 1000, but it is depending on your mesh refinement and so on. So it is better to set some larger value. And now for each point, you should set the inlet and outlet boundary condition. So usually for simulating the water turbines, we use mass flow rate or volumetric flow rate at the inlet. For example, here, I think it is designed to something like 8 meters cubic meter per second, and the range could be, for example, 876, for example. But you can define as many points as you want. Turbulent energy intensity and dissipation rate is set in the default values, but you can also set your values. And at the outlet, there is a fixed pressure which is equal to 0, because it is incompressible case, right? So it uses the kinematic pressure, and usually it uses reference pressure 0 at the outlet. Well, simulation part, the time management. So we will simulate a steady state simulation, but also you can switch to steady state plus transients. So steady state is used to initialize the computation for transient. And if you check this cavitation and choose this steady state plus transient, so this version provides full cavitation model, so transient model with cavitation. So this two-phase solver which shows your cavitation properly, but also it's transient simulation, so it takes some more time than the steady state simulation. So for my case, just a steady state. I can use as many processor as I have, for example 100, but I am on the laptop, so I have only 6 or maybe 4 cores. So I believe 4 cores for the simulation. Numerical order, I can switch, for example, to second for water turbines. Convergence tolerance, so it always during the simulation, it checks how the for example, efficiency and some other parameter is oscillating, and if they reach some steady state solution, it stops the simulation before the maximum iteration is reached, for example. Some numeric, some relaxation can be set. Initial conditions, so initial pressure for incompressible cases usually set to 0. Initial velocity, some reasonable value, usually in the direction of the inlet, it can be, or of the inflow to the domain. Some advanced parameter for meshing, which are not important right now, and post-processing tool, which is quite useful. So automatically you can evaluate, for example, blade-to-blade views right here by simply clicking on plus. Then you will define here which field you would like to visualize. For example, the interesting field is relative velocity with LIC streamlines filter, and at which radial height, for example, just in the middle. The same you can define for the meridional average, and you can see which field you would like to visualize, for example, total pressure. But also you can add more fields to evaluate, and the same holds also for this blade-to-blade views, right? For example, here, for example, some radial coordinates at the hub or near the hub. And additional data files, for example, if you compare this simulation to another simulation, you can add the plot data from the previous simulation, and it will appear in the post-processing report. Okay, anytime you are satisfied with the setup, you should click on apply, and afterwards, and because I didn't set up all steps correctly, so I will use my predefined TCFD file. So I will go smoothly here, Francis Water Turbine. I think I have it here or in this template. So here I have predefined it. I have saved the TCFD file, which I have set up a few hours ago. So I will just click on the setup file, which is defined properly, and you can do it anytime. I will just click on apply. The geometry will appear directly here because in this TCFD file I had already preset this value. Okay, perfect. And now, after the settings part, I should apply this TCFD Manager. And using this TCFD Manager, I simply run the calculation. So first, I will just click on Apply button. And afterwards, I should define the path in which the path and the directory in which whole computation will be stored. For example, my webinar case. So I can create my own directory. Afterwards, I should click on the write case. So whole OpenFOAM case will be written with every important setup, with every compulsory files and post-processing stuff. And then I can just run all by one click using this run all button. And what it is going to do is it will run the meshing process, right? Then it runs the simulation and post-process the results and generate the report. Yeah, anytime you are informed what is happening, so here it tells you, this Turbo Machinery CFD output tells you what is happening at the moment. So now all this geometry and all these files are written, and afterwards we can click run all. Or, for example, what I have done here, well, it is not here, it is my old setup. Yeah, here you can, for example, first you can mesh all. So for example, you can build each component, or you can mesh all at once. During this process, you can, anytime you can visualize the mesh by click on show and to apply, and afterwards the mesh is loaded. It will appear in this render view. When all components are meshed, then we are able to run the calculation manually. Yeah, so if I add this component, and here we can see the results of the meshing anytime. So for example, surface with edges, yeah, anytime you are able to visualize any part of the geometry. Okay, and afterwards I can run the calculation, or afterwards the mesh is run. Okay, so I will jump a little bit and I will go to the end. So this is hidden. Well, so basically you will see this after the simulation is done. So anytime you also see the status bar during the simulation, so you are always informed about the iteration, about the time left, expecting end of the simulation, and so on. You can anytime generate the light report to see the simulation process during the simulation, which is also nice. And automatically at the end, the report is generated. So it can be seen right here in the ParaView, or it can be anytime opened, for example, in your favorite web browser. Yeah, because it is generated in HTML format. So I will go just quickly through this report. So you have a lot of information about the computation, about the mesh. You can see the flow rate during the simulation, residuals, which is also important during the simulation. So in this case, we have set almost 8 or 9 operating points to be simulated. You can see the mesh quality details. You can see the time of the simulation, how many processor was used, which fluid, and so on. Then there are several blocks which shows you a lot of parameters of your geometry of your turbine. For example, the first important parameter is the head for each point, so you can see clearly in the graph or in the table. You can also see the convergence process. The same holds for the efficiency. So here, for example, I loaded some old case, so you will clearly compare 2 or more simulation directly here. You can read the efficiencies. You can check the efficiency convergence if it is okay or if there are some oscillation. But yeah, this is at the end, or this is the operational point which is not designed for this water turbine, for this Francis turbine. You can clearly see the torques and comparison to the old computation, for example, or different, or the measurement, total pressure difference, also important parameter, total pressure per interfaces. So total pressure at the inlet, at the interface between component 1, component 2, and etc. Velocity magnitudes per interfaces, circumferential and meridional angle to, for example, to check the angle of attack to your to your rotor blades and so on. And the last but not least is the cavitation risk. So in sense of the volumes, so here it tells you how many percent of the volume is cavitating, or how many percent of the surfaces of the blades are cavitating, which is really important for designers. And the cavitation index, which is a special cavitation index, and you can see the reference in the user manual. So it's a special cavitation index developed by some guys. Yeah, and because we have defined blade-to-blade view, so you can clearly and nicely see the blade-to-blade view, which is automatically generated. For example, this is the blade-to-blade view near the hub. So radial slices with relative velocity magnitudes and the streamlines. So you can check which operating points attack, or you can to clearly see the angle of attack and which point is the best point for simulation, and so on. This is for the height, 0.5% for each point simulated, and for example here meridional average. So meridional average with static pressure distribution for every computed point. Yeah, so you can nicely compare each point together. Okay, I think my time is almost up. Anytime, of course, you can load the case by click this show results button. So I will just quickly click on it. Then the computational mesh with all computed variables will appear. Yeah, because my computer is computing some other case, so it is not so fast. But it's just because my laptop is a little bit overheated. Great. So if I just visualize, so this is, for example, the pressure, static pressure distribution. You can apply any slices at any parts, or you can visualize streamlines in any part, or just the vectors, and so on and so on. So we can, afterwards, you can play around with the results. Okay, so I think that is all from my side, and I will give my presentation back to Luboš. So Luboš, are you ready for the
Yes,
final part?
absolutely. Yes.
Great.
Thank you, Radek, for your remarkable live example and presentation. It was very nice to see how easy it is to simulate a turbine from
Yes,
scratch.
right.
This time from scratch. It was a pleasure to see this. Okay, so let's move. So
Okay.
I will switch. Okay, it's me again. It's my screen. So
Yeah,
I believe
great.
you
Yeah,
can
yeah,
see
we can see.
my presentation. Okay, so I will quickly finish. So yeah. Uh, yeah. I'm gonna finish with how to get to the machine CFD. So as I already mentioned, the Russian CFD is very transparent because anyone can try Turbomachinery CFD full version for 1 month and decide to take it or leave it after that, after he tries. So it's for this reason it's very transparent. I would like to mention briefly what's our business strategy because it's a little bit different from what's available in the market, especially the commercial codes. So I will only mention that Turbine CFD is paid software and it's always perpetual, so the users can keep it forever. And what is paid for, this is important, is the first delivery and the technical support and updates and maintenance. But there's no licensing, so the users can keep it forever and then can use it for unlimited number of users, jobs, or cores, any number of processors. And yeah, so we have different model. So what is paid for is the first delivery and technical support. And we believe Turbocharged CFD is very affordable. Last year we decided to fight hard for the universities, so we have a special program for the universities at outstanding conditions for them. And private organizations have standard pricing, which we believe is also very, very affordable. So please contact us for the details, and we will gladly tell you everything about the conditions, and we are also very flexible in it. So we will be looking forward to your questions in this. Which brings me to the last section, which is the Q&A session. I have to say I can't see any questions yet. There are no questions, so I would like to ask you to give one or put your question. So we will put your question. We will answer it, and you still have a time. And yeah, I can see one question from Nahalech. So thank you for it. So as I understood, it was a steady state simulation. And what about transient ones? For example, starting up or shutting down, or going from the best efficiency point to part load. Yeah, this question. Yeah, Radek, would you like to answer this?
Yeah,
Or?
I can. Yes,
Okay.
I can. So please give me the presentation.
Oh, of course.
So
of course I will. So
great.
it's here, and I make you a presenter right now.
Show my screen. Okay, perfect. So I will go back to my setup. I will hide this. Yeah. So where is my original setup? No, this wasn't here. Okay, let's say it's here. So I will just open the simulation. So great. This time management here, you can define the steady state simulation or the transient. Yeah, always it starts with the steady state simulation. So if you choose this steady state plus transient, so afterwards, for each point, you should define the time of the simulation. So real physical time of the simulation. So you can use really the seconds for each point, or reasonable is some amount of full revolution of the wheel. So for example, here you can set for, or the computation will simulate 4 physical rotation, full rotation of the wheel. So in this simply is set up here, and also it is simulated for all points. So if you, because transient simulation is more demanding time demanding. So you can, for example, start just with the steady state simulation to find best efficiency point, for example. And for this best efficiency point, you can set this transient and simulate only, for example, one operating point which corresponds to the best efficiency point. And that is all. This is how easy it is. And
Okay.
what maybe I didn't mention is what I forgot is the communication between two components, right? Because you can use there are two main approaches, which is arbitrary mesh interface or so-called frozen rotor methodology. It is defined using the zero value for the interfaces. If you set some non-negative or positive integer, it uses so-called mixing plane approach. So basically, it just split the interface into several rings or lines or strips, and then some averaging is done to communicate between them. And both approaches are provided also with transient, let's say, or roughly speaking, for the transient there is only AMI approach because the rotor part is really rotating. Yeah, so I hope I answered your question.
Okay. Okay, very well. Yeah. So it's always steady state, but it can be also steady state and transient.
Yeah.
Okay.
Next, if I can read the next question, which is what about moving mesh? Is it possible to move mesh in transient run? Basically, the transient run is the really moving the rotation of the geometry. So it is really basically this part is really rotating. So it's so-called solid body motion, and this transient simulation is really full transient simulation. You can see in that case the rotating part is really rotating at the given rotational speed. So this is not just transient solver, but this is really solid body motion of the rotor part.
Yes. Okay. Yeah. This is clear, I think.
Yes, I mean dynamic mesh. Yes, exactly. It is dynamic mesh. So then you can play, for example, videos with which I can show you, for example, which was yeah, YouTube and pump simulation, for example. I hope it will find. Yes, it's exactly this, and this pump simulation was simulated using our software. So it is exactly what you mean, I think. Dynamic mesh, you can see that the rotor bar is really rotating, fully transient solver, right?
Okay.
Yeah, perfect. You're welcome.
Thanks. Yeah. Okay. I can't see any other questions, so I think this is it from us. At least. Yeah. Let's give it a few more seconds. I believe this would be it. So I will, Radek. So I will take back
Sure. Yeah.
presentation. Maybe we should switch off the camera again.
Mm-hmm.
So hello. Yeah. So I think it's gonna be over.
Okay, I'm back too. Okay.
Yeah. And yeah. Let's conclude. Let's conclude. So Radek, anything to say?
Well, just as you saw that the usage of our software is really simple, straightforward. You just load your geometry by few clicks. You define the mesh. You set your operating point, and then you just click on Run All, and you will get the results. You will get post-processing tools, which is really nice, and it is comparable with the standard OpenFOAM. You are not able to achieve all these steps. Yeah, there are a lot of modification. Everything is automated. There are no licenses for number of cores, number of users. It's a great tool, for example, for optimization, because you can really heat up your your hardware, and yeah, it's really great. And I think it is really user-friendly and outstanding software.
Absolutely. Yes. So, okay.
And thank you for watching. And if you have any question, any comments, we are here for you, and we are gladly answer all your questions.
Okay,
so
thanks.
Yeah. From my side.
Yeah. Okay. Thanks, Radek. Thanks. The same from me. So thank you for your attention. Just if you need anything, just send us an email. We will gladly support you. It's our job and also a pleasure. We like it. So we will gladly support you. So let's stay in touch. Let's keep in touch. Thank you for your time. Thank you for your attention. And bye bye. Sometime, someday, somewhere. Yeah.
Okay.
Bye bye.
Nice rest of the day.
Yeah. This is it. Yeah. Okay. Which brings me to the end of the webinar. Yeah.